In this video, we're going to revisit the definite integral. We'll talk about area and Riemann sums. We're going to take a look at the area under a curve, but we're going to take a perspective that might be a tiny bit different than the one that you took when you first saw this problem. I'm going to start by asking, what makes this problem hard? What makes it hard is that the height keeps changing with x. The height varies with x. But what can we do about that? What problem-solving strategy can help conquer this difficulty? We're going to use the method of successive approximations. There are four steps to this. They involve first slicing or partitioning the x interval, because height varies with x, partitioning the x interval AB into pieces, and then on each piece approximating what we're trying to find, which in this case is area. Approximate the area. And we approximate the area where the height doesn't vary quite as much, so we're going to pick a value in that interval and figure out the height there. So approximate the area over a slice. And then we're going to sum. And altogether, this gives us an approximation. So let's start by partitioning the integral from a to b into 3 equal pieces. Then each of these pieces will be of length delta x equals b minus a, the length of the interval, divided by 3. And I've labeled the points x naught, x sub 1, x sub 2, and x sub 3. Let's try and say what those are. Suppose you didn't have a picture. You would say x sub naught, x naught equals a, the left-hand endpoint. And then what's x sub 1? Well, that's a plus delta x. And x sub 2, that's x sub 1 plus delta x, or it's a plus 2 delta x. And x sub 3 is b, but also it should be a plus 3 delta x. Let's see if that works. It must, right? So it's a plus 3 times delta x, which is b minus a over 3. And the 3's cancel, so we get a plus b minus a equals b. Okay, so we've described everything that I've drawn. And now on each interval, I choose some point in the interval and figure out the height at that point. So what I'm going to do here is, on the left-hand picture, I'm going to choose the left-hand sum. I'm going to choose the left-hand corner of each left-hand endpoint of each interval, look at the height there, and say, let's assume that that was the height throughout that whole interval. So in the next interval, I pick the left-hand corner and say, let's assume that the height there is the height in that whole interval. And likewise, in the last. So this is called a left-hand sum. We could do the same thing and get a right-hand sum. On the right-hand side of the page, I've drawn a right-hand sum. Both of these approximate the area under the curve. Neither one is the area under the curve. What could I do to get a better approximation? Remember, we're using the method of successive approximations. Well, I could, instead of using 3 equal pieces, I could choose 10 equal pieces, or 100, or 1,000, or 1,000,000. And in general, as I'm increasing the number of slices I get, I'm increasing the accuracy of my approximation. So what I'm going to do next is write a partition of the interval from A to B into n equal pieces and see what we get. So now we're going to partition the interval from A to B into n equal pieces, because then we can let n grow without bound. So each piece is of length delta x, where delta x is b minus a, the length of the whole thing, divided by n. And let's use that same numbering system. Let's call this x naught, x sub 1, x sub 2, x sub 3, and we keep on numbering until we get to x sub n. So let's see if we could describe the type of labeling we just used. So again, x sub 0, x naught, is a. And x1, well, we move delta x over, and we've already described what delta x is. So it's a plus delta x. x2, a plus 2 delta x. x3, move another delta x. So we could say, in fact, a sub k x sub k equals a plus k times delta x. And in fact, if we say that, where k equals 0 all the way up to n, we've just described how to label everything. So really, let's go back and erase what we don't need. Really, we don't need this, and we really don't need that either, right? This says it all. Okay, so what we want to do is in each interval, we're going to choose the height somewhere in the interval, and let's assume that it's constantly that. So I'm going to choose the right-hand endpoints. So in each interval, I'm going to the right-hand endpoint and saying, let's assume that that was the height all the way through. And we can see that that's a very good approximation. So if we want to write down the area, what we want to do is slice that we've done and approximate. I want to approximate the area of the kth slice. So let me focus on one of these, an arbitrary one, and let's say that's the kth slice. So there it is, and we're going to be approximating this area by the area of a rectangle. Okay, so it's approximately, so let's suppose that this is x sub k. Okay, so it's approximately f of x sub k times delta x. And we want to add this up. First slice, the second slice, the third slice, all the way up to the nth slice. So we'd say that the total area is about equal to the sum of the areas of the rectangles, f of x sub k times delta x, where k starts at 1, that's the first slice. Remember, we're using f of x sub 1, right-hand endpoint, as the height, to n. So total area is that. And if we take the limit as n grows without bound of the sum, k equals 1 to n, f of x sub k delta x. That gives us the integral from a to b of f of x dx. That, in fact, is the definition of the definite integral. It's the limit of this Riemann sum. So this is called the Riemann sum. And the definite integral is defined in this way. This is the definition of the definite integral. Now, in order to apply this to different situations, we're going to really need to understand each of the pieces of this, because we're going to start by writing Riemann sums. And it's the Riemann sum that will tell us what the definite integral is that we're interested in. So let's see how the left and right hand side of these remind us of one another. For instance, notice that on the right hand side, we've got A and B. We never see that on the left. So where do they come from? Well, the left-hand side says that we're going to start with f of x sub 1. And x sub 1 is a plus delta x. Now, as n goes to infinity, what happens to delta x? Delta x is going to 0. So x sub 1, as n goes to infinity, x sub 1 tends towards a. And the last x that we use is we're looking at f of x sub n. So x sub n is a plus n delta x, which is a plus n times b minus a over n, little stray piece of white there, equals a plus b minus a equals b. So the a and b come from both the definition of delta x and the definition of x sub k. So each time that we write this Riemann sum, we're going to need to also say what delta x is and what x sub k is. Otherwise, there's no way for anybody to know from what's on the left how to get the endpoints of the integral on the right. Now, when I think about the integral on the right, I think of the integration sign as an elongated summation. It says I'm summing up things that look like f of x, here that reminds us of the f of x sub k, times delta x. So this reminds me of the delta x. So I'm summing up the height times the base, if I'm thinking about this particular example. Okay, let's see how we can use these ideas in other examples.